Okay, so we are going to do our force and weight equation practice. So this is notes on both force and weight, and then we're going to do some equation practice where we're going to solve some math problems. So let's just go ahead and go with our two different major definitions that have to do with both force and weight and understand the difference between mass versus weight. So first off, the definition of mass. Mass is the amount of matter that makes up an object. Okay, so what's important to remember is your mass doesn't change when you go away, or if you, as long as you stay on Earth. It would only, and even if you go to the moon or Mars or another planet, your mass stays the same. So most of us will be on Earth our whole lives, but if we do happen to leave, your mass doesn't change. Now, obviously, you can add mass by lifting weights or losing weight, but your immediate change doesn't happen just by moving to different planets around the solar system that have different gravity. So I'm going to put in parentheses, doesn't change when you leave Earth. So mass always stays the same. Okay, so the other thing that we always confuse it with is the word weight. So weight in physics is a force. Okay, we measure it in newtons, so it's a force. So weight is the amount of force an object has based on its mass and gravity. Oops. So mass versus weight, two different things when we're talking about physics concepts, okay? So let's do the equation for weight, just so we can make sure we have it in our notes. So we know weight is a force, and we have already learned that force equals mass times acceleration. So remember, mass is a kilogram, acceleration is a meters per second squared. So we get a kilograms meters per second squared. So what's important to remember is a meters per second squared is also an acceleration, or is gravity. So gravity, when we're talking about gravity here for weight, it is an acceleration. So technically we have a mass and an acceleration, which shows us that weight is a force. So the equation is W equals M times G. Okay, so when we talk about our units, just like we've done before, our mass is in kilograms. We're multiplying that by a meters per second squared, okay, because that's a gravity is an acceleration. That gives us a kilograms meters per second squared. So technically, we have a kilograms meters per second squared, but we change that to what we call a Newton, so we don't have to say kilograms meters per second squared every time. So a Newton, if it's broke down, is a kilograms meters per second squared, because we're multiplying a mass times the gravity or an acceleration there. Okay, so it does have a circle. When we're solving, if we want to solve for mass or gravity, we can go weight on top, and then we have mass and gravity on bottom. So just remember, when using the circle, if I want to search for weight, I cover up the W, I get M next to G, they're next to each other, so that means I'm multiplying them. If I'm looking for mass, I get weight divided by gravity. And at times, I could be looking for gravity. So I might say, hey, you're going to go to the moon. What's the gravity on the moon? And I'll give you the weight and the mass of the object. And you tell me the gravity on the moon or whatever planet it is. Okay? So remember, it is the same as a force. Weight is a force. So let's go ahead and do the equation for force. And we've already written down the definition of force in our last notes, but in parentheses, I'm going to put push or pull just to have it there in our notes if you need it on an object. So that's those applied forces and tensional forces and friction, all these forces that act on an object. Okay, so the equation for force is, we've done it, but we're going to do it again. F equals m times A. So again, the units are exactly the same as our weight. We have a kilograms times a meters per second squared, because that's acceleration unit. Multiply them together, you get a Newton. Or break it down, a kilograms meters per second squared. So that is our units for force and weight being the same thing. We're using newtons for both of them. We can also use the circle for the force equation. I haven't drawn a circle in a while, you guys. It's not very straight. All right, so mass times acceleration. So again, same deal. If I'm looking for the acceleration, force divided by mass, cover it up, I get force on top, mass on bottom. So force divided by mass. If I'm looking for the mass, force on top, acceleration on bottom. So force divided by acceleration. And if I'm looking for force, we already know, next to each other, mass times acceleration. Okay, so let's talk a little bit about net force before we do our other equations, because net force is important because we did those free body diagrams and we didn't use numbers. We used arrow size or magnitude. We didn't actually put numerical values on that. So when there are numerical values, we have to understand how to get the net force on acting on an object. Okay, so let's do that. Net force on an object. Okay, so let's just use a box for sake of making it easy. We have a box and we're saying let's have two people pushing in the same direction. So we'll give this a value of 10 newtons and this a value of 12 newtons. Okay, so if they're in the same direction, no matter what, to get net force, net means total amount of force. So I'll just go ahead and write that, total force. So to get total of anything, we add. In any math problem, if I say give me the total of all of these objects together, we're going to add them together. So in this case, the total that we're going to get is 10 plus 12, because in the same direction, okay, they're both going in the same direction. We're going to go 10 newtons plus 12 newtons, and that's going to give us 22 newtons of net force on the object. So adding together. All right, so let's go ahead and make another square. Goodness, guys, I can't draw a straight line today. So this time, let's say they're going in opposite directions. So we're going to go 10 newtons to the right, and we're also going to go in the opposite direction, 12 newtons. So anytime it's going to the left or down, we've got negative. Anytime it's going to the up or right, we have positive. Remember that. So I'm going to assign that as a 12 negative. Now in opposite directions, we're still adding. So just because we changed the direction doesn't mean we're not adding. We're still adding. We're just this time adding a negative. So a lot of people will say, well, isn't it the same as subtracting? Well, sure. If you're working it that way, it can be like that. Sometimes people just automatically do that in their head, which is fine. But in this case, we're going to set it up just like we would, 10 newtons plus a negative 12 newtons. So essentially, it's taking 10 minus 12 would give us negative 2, or 10 plus a negative 12. We're going to get negative 2 newtons. Now, direction matters, so we got to remember that this would be to the left. I'm just going to go ahead and put that. And actually over here, since this was a positive, we'd know it was moving to the right. Here, since it's a negative, we know it's moving to the left. So more newtons on the left equal movement to the left. Pretty obvious, right? Now, there are times where they might have forces acting in a right angle direction. So maybe coming at each other like this. Okay, so we've done this before in displacement, if you remember. Anytime things were coming at a right angle, we had to figure out the hypotenuse of the right triangle, which was like C over here, remember? So it's like the same if we had, let's say, let's go right here is 12 newtons, and here they're going to go 10 newtons. Now, still both positive, right? Because this guy's going up and this guy's going to the right. So both of them are positive. Now, if one was going down, I would call one of them negative, but I'm not because they're both positive still. I am going to be doing the right angle method. Remember, we're looking for that hypotenuse, which is C. So we're going to call this A, B, and C, which means we have to do A squared plus B squared equals C squared, that Pythagorean theorem. Okay. So I'm going to plug in, and we'll just call 12A 10B, and we're going to look for C. So we're going to say 12, and technically this is a Newton. So 12 newtons, and I'm going to put parentheses around it and the squared outside. That reminds me I have to square everything inside. Plus my B, which is 10 newtons, so 10 newtons squared equals C squared. So I keep bringing the C squared with me the whole time because I don't want to get messed up and forget about the C squared. So now I'm going to square 12, and I know that's 144 newtons squared because I also have to square the newtons. Now remember, that's not showing me that I have to square the 144 anymore. I already squared it, the 12, and now I'm at a newton squared. Plus 10 squared is 100 newtons squared, so just the unit is squared now, not the number anymore, equals C squared, so I'm still bringing that down. So now I get to add 144 and 100 to each other, and that's going to give me 244 newtons squared. So notice I didn't do anything yet. I just added them. I didn't get rid of the squared yet. Equals C squared. So this is our clue. We're looking for C by itself. We're not looking for C squared. So to get C by itself, I need to get rid of the squared. So by getting rid of the squared, I have to square root it, which is the opposite, which means I do that to both sides. And so now I've square rooted C. I can see that C is going to equal, because it's no longer squared. Now I have to take the square root of 244. So I'm going to plug it into my calculator here, and I'm going to get 15.62. Or if you wanted to just go with 0.6, we'll do that. And that's going to be newtons. So I'm going to circle that as my answer. And that just tells me that I'm going, since we're pushing here and pushing here. Now, there's this really fancy trigonometry type way that we could figure out exactly the angle that it's going, but we're not going to do that. But in general, since it's pushing just a teensy bit more this way than it is upward, we're going to end up with some sort of angle kind of going off that direction. And that angle is going to be 15.6 newtons. So that would be the direction it goes, and that would be the amount of force acting on the object. Okay? So that's how that works out there for net force. And we'll practice more examples of that. Okay, so let's change the page, and we're going to do some examples of force. So, get my camera back up. So, examples. So this time we're going to solve for some of the different variables here. And we're going to mix up both force and weight problems. Okay, so number one, what is the weight of a 67 kilogram object? Okay, so it's been a while since we've solved problems, so I'm going to go to the process here. Remember, circle what you need and underline what they give you. What is the weight is what I'm looking for. And they give me the mass, but they didn't give me a third number. So some of you might say, I can't find the other number, but remember, we know this other number. So just for purposes of having this, I'm going to put it over here. I'm going to make the weight circle over here. And I'll also add the force circle. So when we get to force problems, we'll have that. So if I'm looking for weight, I know I need a W, an M, and a G, which is weight, mass, and gravity. So weight is what I'm looking for, so that's going to be X newtons. My mass is given to me at 67 kilograms. And gravity is not given to me, but I know this because we've used it. It's 9.8 meters per second squared. Remember, it's an acceleration, so you got that meters per second squared there. So we know that if I'm looking for weight, cover up the W, get M times G, mass times gravity. So X newtons is my weight, so X newtons equals my mass, 67 kilograms, multiplied by gravity, 9.8 meters per second squared. You can put a little dot there if you want to instead of parentheses, but I just put parentheses to make it clearer. Now I just multiply 67 times 9.8 equals 656.6. And that's newtons. Remember, it's a kilograms meters per second squared or a newton. So that is the weight of an object that has a 67 kilograms. Now remember, weight is not the same as the weight in pounds. So you might go, whoa, that's a huge number. No, that's not the same as 656 pounds. That's how many newtons of force are pulling them to the ground based on the gravity of Earth. Okay? Number 2, what is the acceleration? So what is the acceleration? So we're going to look for something else. Of an object. Sorry, I'm not very clever today with the types of objects. Everything's just an object or person. With 256 kilograms of mass and 650 newtons of force. Okay, so in this case, we're going to go through our method. We're going to circle what we need. What is the acceleration? An object with 256 kilograms of mass and 650 newtons of force. So I still need an F, an M, and an A. I need all three of those variables, force, mass, and acceleration. So I'm looking for acceleration this time, so that's going to be X meters per second squared. I'm given a mass of 256 kilograms and a force of 650 newtons. So what do I need to do? I need to plug it into my equation looking for A. So if I forget how to rearrange the equation, I can cover up A and I get F on top of M. So force divided by mass. So my equation would look like this. Acceleration equals force divided by mass. So I'm going to take those numbers and plug it into this equation. X meters per second squared is my A. My force is 650 newtons. I'm going to divide that by 256 kilograms. So I can plug it in and go 650 divided by 256 gives me 2.5, and I'm going to round up 2.54 because I rounded up the 9 here. Rounded up the 3, sorry, because it was a 9. And it's a meters per second squared. So just out of knowledge, reminding you, how did we get a meters per second squared when we took a newton divided by a kilogram? Remember, if you break down a newton, it is a kilograms meters per second squared. So on top and bottom, I have a kilograms. So it leaves me with a meters per second squared. And that's how I get that as my unit. Okay? So that's the acceleration the object's going with that mass and that force. All right, number 3. 3, what is the mass of an object? So let's find mass. What is the mass of an object that is pushed with the force of 225 newtons and accelerates at 4.5 meters per second squared? All right, let me move up my camera a little bit. So now we're looking for mass. So what is the mass? So we circle what we're looking for. of an object that is pushed with a force of 225 newtons, so I underline that, and accelerates at 4.5 meters per second squared. So I'm given a force and an acceleration. So looking at my variables, I still need an F, an M, and an A, force, mass, acceleration. This time I'm given 225 newtons of force. I'm looking for mass, so that's going to be X kilograms. So X is what I'm looking for. Acceleration is given to me at 4.5 meters per second squared. So to find out what my equation looks like, I'm looking for M, cover it up. I get force on top of acceleration. So force divided by acceleration. So my equation would look like this. Mass equals force divided by acceleration. And now I plug in these numbers into this equation. So my M is X kilograms equals my force on top, 225 newtons, dividing it by my acceleration of 4.5 meters per second squared. So now I can plug it into my 225 divided by 4.5 equals 50. And I know I'm looking for a kilogram, but I can just check it by breaking down the Newton to a kilograms meters per second squared. Meters per second squared on bottom, 1 on top, leaves me with a kilogram, which is what I'm looking for, so I know I'm doing it correctly. All right. Okay, let's do another one. So this is going to be a two-part one. So we're going to combine net force and looking for one of the variables in the equation. Okay, so first we want to, let's see, find the acceleration on a 20 kilogram box. Hey, switching it up. That is pushed with 25 newtons to the right and 40 newtons to the left. Okay, so we got to think of that first. So we want to find the acceleration on a 20 kilogram box, and we're given two forces. So we're going to have to figure out net force before we solve in the equation, because we can't have two forces. We need the net force. So the first thing I'm going to do is draw out what's happening so I can make sure I have the directions and the positives and negatives correct. So it's going 25 newtons to the right. That's somebody pushing 25 newtons. So remember, right is positive. And 40 newtons, so I'm going to give it a negative because it's to the left. So we have a 25 to the right, and we have a negative 40 to the left. So remember, net force means add them together. So really simply, we're going to say 25 newtons plus negative 40 newtons equals, now if I were to plug it into a calculator, I could do it, or I could just do in my head. I know 40 minus 25 is 15, so I'm going to do negative 15 because I know there's more negatives than positives. Negative 15 newtons is the net force on the object, and that means it's going to the left, just to remind you, because it's negative. Okay. Now, I'm not done, though. I want the acceleration. Right? Acceleration means how is it changing velocity? And so now I have to finish the problem by figuring out what my variables are, because I have a force, a net force now, and I have a mass of 20 kilograms. I need to find A. So my new net force is negative 15 newtons. So I'm going to plug that in for my variable. My mass is 20 kilograms. And my acceleration is what I'm looking for. So it's going to be X meters per second squared. So now I need to use this to figure out, okay, I'm looking for A. We've already done this before, but just as a reminder, cover up A, and I get force divided by mass. So just, I'm going to write that down so I remember. F divided by M. Now I'm going to take these and plug them into the equation. X meters per second equals, my force is on top. Remember, it's a negative, so don't forget it. Divide that by my mass, which is 20 kilograms. Okay, so now I could plug it into a calculator, not forgetting my negative. So there, that's over there showing me I did the negative. Divide it by 20, and I'm going to get negative. There's the negative over there because I'm dividing by a negative by a positive, so it's going to be a negative number. Negative 0.75. I know it's an acceleration, so it's a meters per second squared, but I could also break down my Newton into a kilograms meters per second squared. Cancel kilograms, cancel kilograms. That leaves me with that acceleration. So acceleration can be negative as well, remember? So direction matters in acceleration. So typically if you have a negative force, you're going to end up with a negative acceleration. Okay, because you can't really have a negative mass. That doesn't work because negative mass isn't something. It's kind of like time. You can't have a negative time. Okay, so those are our examples, and that is it.